All right. So how's it going, everybody? Hope everybody's spring break was good, and hopefully you guys got some good rest. I did see a question that somebody had. Adam had a question here about the chess tournament. So we didn't have enough people show up to our last chess tournament. I don't know what happened. Maybe it's just difficult in terms of the communication and all that. It would be great if we could have a chess tournament tomorrow, because that's actually the last day of my subscription, and we'll see if that works out. I mean, if everybody likes to do these tournaments, I can renew my subscription, but I'm not going to do that if nobody's actually showing up. So, yeah, so let's go ahead. Adam, would tomorrow sometime be good for the chess tournament? And what time would be good? Like, for me, I think kind of like right after school would be good, which is, what is like right after school? Like 3:15, 3:30 or something like that. That would be good for me. Just because the evenings get kind of, so 3:30, yeah, that would work great for me because the evenings get kind of sketchy. So let's do that. We'll have a tournament tomorrow, 3:30. I'll send out the invite. Hopefully we get enough people, and if not, whatever. It is what it is. So I'm just going to set that time. Adam, you can tell other people that we're going to have a chess tournament 3:30 tomorrow, Tuesday. Okay? Cool. Thanks for reminding me. I was a little disappointed we didn't have enough people show up. There was only 3 of us last time, so we just played a couple games and that was it. So, all right. And it's best, I know some of you guys have never played on chess.com. It's best if you actually play a few games first to get the feel of it before you enter into the tournament, although it's no big deal. That's, it's whatever you guys want. So anyway, welcome back. Hopefully you guys all had a good spring break, and hopefully you guys got some rest and had some fun time. All right. And let's see, if you guys have any good stories from spring break, go ahead and tell me. Otherwise, like for me, my spring break was kind of boring. Just ended up staying home, doing my taxes, did a little bit of gardening. It's kind of crazy how cold it is these days. But yeah, I ended up still doing some gardening and taxes, and that was just about it. And then also catching up on all my grading and all that stuff. But anyway, here we go. So last time we were talking about intensity of sound, and we're going to go ahead and jump into that today. I think I'm going to go through the homework. You guys probably already forgot it, so I'm going to try to go through it relatively quickly. And let me see, that was 12A, I think it was, 12A. And see, the thing is, for this particular chapter, it's kind of short, so we're just going to do today, talk about decibels, and then we're going to actually, tomorrow, we're going to start in with chapter 13 and talk about light. So the reason I'm doing that is rather than having a test, because this unit or this chapter is so short, we're just going to include it in the next test because we just had break. I don't feel like, this week having a test. This just seems a little bit ridiculous, or it wouldn't even be enough for a test. It would just be a quiz. But I think we're just going to add it into the next chapter. We're talking about light, so we'll have a test on light and sound together, and that'll pretty much be it. All right, so today, first, let's go over the homework. I believe it was page 665, and that's numbers 2 to 5, okay? So number 2, let's just jump right into that one. And let me see, I got all your comments got pushed down to the bottom, so I'm going to see if I can see if there's any more comments here. Okay, all right, cool. So number 2, if we can get this on here, here we go. So at a maximum level of loudness, the power output of a 75-piece orchestra radiated as sound is 70 watts. So it's looking like about 1 watt per instrument, which is pretty loud. What is the intensity of these sounds to a listener who is sitting 25 meters from the orchestra? So that's a pretty good distance away too. Obviously, if you were up close, it's going to be a lot louder. But here we go. So that's going to give us, where are we? Here we go. So number 2, we have a power of 70 watts. We have a distance, which in this case is going to be a radius, because it doesn't matter which position you are, as long as that, distance is the same, that's going to be the same intensity of sound. And so that radius is going to be 25 meters. And we just have the simple equation for your intensity. And you can label that as I or intensity, however you want to write that, is going to be equal to the power divided by the surface area of that sphere, which is 4 pi r squared. So in this case, it's going to be your 70 watts divided by 4 pi 25 meters squared. Okay, and the units we're expecting to be watts per square meter, which is exactly what they are, watts per square meter. And let's scoot this over. So that's going to be 70 divided by, and we're just going to put this all in parentheses, 4 pi times 25 squared. And that gets us 0.0089, and that should be your answer. We have, I believe we have, do we have no, we actually have 3 significant figures here. There are 3 significant figures, so it should be 0.00891. And our units, watts per square meter. Okay? So, if you guys have any questions or anything, just go ahead and stop me there. Who is JHDVDH? I don't know. Cool. Somebody is going to be joining our chess tournament, maybe? I don't know. It would be great if we could have lots of people. Ideally, get at least 10 people. That'd be great. Last time there was only 3 of us, which wasn't enough. All right, so number 3. Here we have, once again, for number 3, we got a similar kind of question here. We got scientific notation. Yes, absolutely. You can use scientific notation. There's no need to. It's totally up to you unless it says exactly, use scientific notation. So in that case, that would be 8.91 times 10 to the minus 3, right? 1, 2, 3 watts per square meter. And today we're going to kind of, the goal of today is to relate these intensity values. And nobody has any, well, at least most people don't have any idea, well, what in the world does that really mean? 0.00891, is that a big number? Is that a small number? How loud really is that? And so today we're going to relate that to decibels. And so we're going to talk about that today. But just as a reference, if you had 1 watt per square meter, that's a loud sound. So once you get up to 1, that's kind of at the threshold of pain. So anything bigger than 1 is going to hurt your ears. Anything less than 1 is going to be somewhat normal. So 1 is kind of a very big number in terms of sound intensity. All right, anything bigger than that is definitely going to hurt your ears. So here we are. We are number 3. If the intensity of a person's voice is that number, at a distance of 2 meters, how much sound power does that person generate? So we have this time an intensity, and we're solving for power. So go ahead and write that. Intensity is 4.6 times 10 to the minus 7. So clearly it's less than this, watts per square meter. And we have a distance of 2 meters, and we want to know how much power. So what's the power? Okay, so similar kind of situation here, but instead of solving for the intensity, now we're solving for the power. So we're going to need to rearrange this equation to solve for the power. So all we're going to do is multiply both sides by 4 pi r squared, right? So that's going to get us power equals the intensity times 4 pi r squared. So write that down here. Power equals the intensity times 4 pi r squared, which is this 4.6 times 10 to the minus 7 watts per square meter times 4 pi, I'm going to run out of space here, times your r, which is 2 squared. So let me just go ahead and turn that into 2 squared right now. So 2 squared is 4 and that's 4 meters squared. Okay, so we'll just plug that in our calculators. That's going to get us 4.6 e negative 7 times 4 times 4, so that's 16, and then pi. All right, so it should be 2.3, and I believe this time we do have only 2 significant figures. Yep, 2.3 times 10 to the minus 5. Now, what are the units for power? This is 2.3 times 10 to the minus 5. And what are the units? Well, we can remember the units for power in general, or we can just look over here and see what the units are, right? So we have your watts per square meter times square meter. The meters squared cancels out, and we're just left with watts. And if we recall, well, yeah, watts are generally the units for power, right? So any kind of power that we're talking about, that's going to be measured in watts. And a watt is a joule per second, if you guys remember that, joule per second. All right, so next we have number 4. Number 4 is how much power is radiated. So once again, we're solving for power. How much power is radiated as sound from a band whose intensity is 1.6 times 10 to the minus 3 watts per square meter at a distance of 15 meters. So same exact problem that we just solved, right? There is just a different kind of sound here. So we're still solving for power, right? And our equation is still going to be I times 4 pi r squared. And we can just plug in the values from the problem. It tells us that your intensity is, let's just plug it in this way, 1.6 times 10 to the minus 3 watts per square meter. And then 4 pi r squared times, we'll just write 4 pi. And then r was 15. So 15 meters squared. So that's going to give us let's see, 1.6 negative 3 times 4 pi times 15 squared. And you can just put the squared right in there. The order of operations will work correctly for this. And we're getting 4.5. 4.5. And this, once again, is power. So this is 4.5 watts. So although the power of the individual instruments or whatever else, or the speakers and all that might be rated more than 4.5 watts, that's a measure of how much sound is coming out. Clearly, these speakers are going to be wasting some amount of energy in that. They're not going to be transmitting 100% of their energy into sound energy, but this is the amount of sound energy that's coming out of them. Okay? All right, so that gives us one last problem. Let's do number 5 here together. Flip it over. Number 5, we have, now number 5 is a little bit different, I believe. For number 5, let's see. It says the power output of a tuba is 0.35 watts. At what distance is the sound intensity of the tuba 1.2 times 10 to the minus 3rd watts per square meter? So let's just write down what we know so far, the power output. So we have power, 0.35 watts. And we have sound intensity. It's going to be 1.2 times 10 to the minus 3 watts per square meter. And so it says at what distance, and we think, okay, what does that mean? Well, at what distance? What units is that? Well, or what variable is that? That's going to be your R, right? You want to solve for R in this case. And so we're going to take that equation and now rearrange it to solve for R. And we had, let me just use the previously rearranged equation that we had. We had intensity that was times 4 pi r squared equals your power. And we want to solve for R. So I'm just going to take this stuff, your I 4 pi, and bring it to the other side, and that's going to get us R, oops, let me move this. That's going to get us R squared. So if I move your I 4 pi and take this to the other side of the equation, so we're going to divide both sides of the equation by 4 pi I, that's going to get us P, that's going to is R squared equals P over 4 pi I. Okay? But that's not actually getting us R itself. We need to take the square root of both sides. So R is the square root of P over 4 pi I. So now we just plug in some numbers. We put in our 0.35 watts for P. We put in our 1.2 times 10 to the minus 3 for I. And that will get us the square root of 0.35 watts on top, 4 pi times 1.2 times 10 to the minus 3. And of course, watts per square meter. Okay, our watts over watts are going to cancel out. We're going to be left with square meters in the bottom, right? But it's the bottom of the bottom, so it's going to be square meters in the top. And that's going to, when you take the square root of that, that's going to get us units of meters for our final answer. So the answer should be in meters, which we would expect because this is for the radius or for the distance. So let's go ahead and plug in numbers and see if that works out. So we have, over here, we have 0.35 divided by, and we can put this all in parentheses or do multiple divisions. Either way works. Let's just go ahead and put it in parentheses. So 4 pi times 1.2 e negative 3. And we get 23, but that's not a final answer because we need to square root it. And you can do it all in one step, but it gets a little bit, a lot of stuff all in one line. So I like to do it this way. So I'm going to take the second square root of my answer, and there we go. That's our final answer, 4.8. And we do have only two significant figures, so that is it, 4.8 meters. 4.8 meters. All right, so that's your homework that you guys did like ages ago. And so hopefully you guys did fine on those. If you guys have any questions, just feel free to ask, but you guys probably already figured out all those, whether they're right or not. I'm going to go ahead and jump into the new stuff then. If there are no questions, I'm not seeing any questions here on the comment section. All right, but let's go ahead and do the new stuff, which is, oh, and by the way, as we're transitioning, I do want to say that I did upload 2 documents. I tried to take off the old document, but apparently it didn't work. So you guys have 2 different documents there because I decided, I initially had like a homework document, and then I realized, well, hey, it's not, I don't have any sample problems on there for you guys, so I wanted to have a homework document that had some sample problems on it. So I'm going to go ahead and go through a couple of different sample problems today, but just keep in mind there are 2 different documents. I'd like you guys to do the new one, the long one, that has the sample problems on it, but the homework problems are pretty much the same, okay? So that's the only difference. One other thing, so you read through the book, it's going to talk about a little bit about resonance, and I uploaded, or I give you a link to a really cool video of the Tacoma Falls Bridge, which is really, really cool. You guys definitely have to watch the video. I think it's about 5 minutes, just 5-minute video, super, super cool video. And then there's a whole bunch of different videos on YouTube that are about that. I think this is just some British guy talking about it. So watch that video. It's a bridge that was built, unfortunately, that had just the wrong resonance frequency. And so it was able to vibrate a whole lot when the wind blew, and it eventually fell down. And you get some actual, don't know what happened there. Okay, so sorry about that, guys. I think my connection got severed for just a quick second there. So anyway, so we've been talking about sound, right? We've been talking about sound in terms of the intensity, in terms of the power, in terms of the distance, but we haven't really talked about loudness. it turns out that loudness in general, and this is not exactly correct, but intensity is not the same as loudness. Intensity is got a specific definition with what we've been dealing with, right? It's specifically got to do with that power and the amount of that power that's distributed at a certain point in time. So intensity is great because it tells us that as you go away from a source at any distance, so if you're at one particular distance, you can talk about a particular amount of that sound power at that particular point, okay? So if two things have exactly the same intensity of sound, they have exactly the same loudness. But that said, loudness is not the same as intensity. What do I mean by that? Something can be 10 times as intense, but your ears are not going to feel it as 10 times as loud. Okay? So something can be 10 times as intense, and instead of it being 10 times as loud, you might only feel it is, let's say, twice as loud. Okay? And so it turns out that loudness is more or less on a logarithmic scale. Okay? Not exactly, but it's more or less logarithmic. Well, what does that mean? That means that as the intensity increases a whole lot, the loudness only increases a little bit. And so it might take a very, very large increase in intensity for you to have a noticeable increase in loudness. And that's good because it enables your ears to hear a much larger range of sound, right? If your ears, if your loudness and intensity were this kind of linear relationship, then you wouldn't be able to hear as much of a range of sound. Right? And so it allows for a greater range. And that range of sound is going to depend on the frequency. It's going to depend on the specific tone or whatever that the pitch of the music is. Okay? Now, or sound or whatever. So this range is more or less, now the range depends on your age. Obviously, younger people have a greater range than older people. As you get older, you lose a little bit or maybe a lot of your hearing. But the range more or less officially goes from a range of 1 times 10 to the minus 12th to 1 watts per square meter. All right? And so this right here, this 1 times 10 to the minus 12th, that is known as the threshold of hearing. Oops. Threshold of hearing. So in general, that's about the softest sound that you can hear. You can hear something around 1 times 10 to the minus 12th, but not really anything quieter than that. That's about the quietest possible sound. All right? And this is known as, this is not the loudest sound you can hear. You can obviously, hear even much, much louder sounds, obviously. There's no limit to that. At some point in time, the sound might be so large that it'll just like cause your ears to explode or something like that. But this is known as the threshold of pain. Okay? So 1 watt per square meter of sound intensity won't necessarily immediately cause you pain, but it very quickly will. Okay? And so the louder it is, so once you get to 1, that's more or less at where it starts to hurt a little bit. And then once you get to 10, 100, that's going to hurt quite a bit. Okay? So the larger this is, the more it's going to hurt. And it starts to hurt right around 1. Now, this range is just approximate. Like I said, younger people can typically hear more than that. They can hear even quieter sounds, and it depends on the specific frequency of the sound. So certain pitches you can hear better than others, and so I think right around, let's say 1,000 hertz, and your book talks about this, right around 1,000 or 2,000 hertz, you can hear even quieter sounds than this, But if you're down around the limits, so your hearing typically not only has a volume range, but it also has a frequency range. So your frequency range is going to be from 20 hertz to about 20 kilohertz or 20,000 hertz. Okay? And so if you're in the middle, you can hear things a lot quieter. Once you're on the edges, so if you're at 20 hertz or 20,000 hertz, then there's no way you could possibly hear this. All right? You're going to need something significantly louder to be able to hear something that's 20 hertz or 20,000 hertz. Okay? And your book has a big, nice graph that demonstrates that. So it's pretty cool. All right. So with that said, because your sound itself, so loudness is really a logarithmic thing, and because we have this extremely large range, right? 1 times 10 to the minus 12th all the way up to 1, that's 12 orders of magnitude. That's an enormous range that our ears can pick up. And so because of that, we need a different kind of scale that can make sense of this loudness a little bit better than just simply intensity. All right, and so they came up with the Bell scale. All right, so a Bell scale. So Alexander Graham Bell did a lot of stuff with sound and all that, and so he came up with the Bell scale. So a bell is equal to the log of the intensity of the sound, okay, so whatever your sound intensity is, divided by 1 times 10 to the minus 12th watts per square meter. Well, why is that? Why is it divided by this 1 times 10 to the minus 12th watts per square meter? Because this is that threshold of hearing, okay? So that if, let's suppose you're listening to something that has an intensity of 1 times 10 to the minus 12th. Well, in that case, if it's 1 times 10 to the minus 12th intensity, that's going to be 1 times 10 to the minus 12th divided by 1 times 10 to the minus 12th, or 1, and the log of 1 is 0. Okay? So if you have, basically, you have at the threshold of hearing, you have a sound loudness of 0 bells. Now, you probably never heard of bells before, and you're like, Mr. Katz, what in the world is this bell stuff? Because for some reason, and I don't know why, but for some reason somebody thought it would be dumb to talk about bells. They like the idea of decibels. Well, we all know exactly what a deci is. So deci is a factor of 10 smaller than that. So if it's a factor of 10 smaller than that, we can define a decibel as 10 times this. So decibel equals 10 times log of I over 1 times 10 to the minus 12th watts per square meter. Okay? So that's what a decibel is. And you can abbreviate it as lowercase d because deci is just a prefix b. So decibel. And the bell is the real units, but nobody ever talks about bells. Everybody talks about decibels. Okay, so guys, this is really weird. I don't know why I'm getting kicked off twice here. And so apparently having some connectivity issues. Really, really sorry about that. I don't know how this is going to look when I upload it and watch it myself. But anyway, really sorry about that, guys. No idea what's happening. Anyway, so decibel is related to the bell just simply by a factor of 10. All right. I know nobody ever talks about the bells, but a bell is the original definition of, your original loudness units. And so but we normally talk about decibels, which is just 10 times whatever your bells are. Okay? Just like if you're talking about 1 meter and you want to know how many decimeters are in 1 meter, well, there's 10 decimeters in 1 meter. Okay? So there are 10 decibels per bell. All right? So your decibels are going to be 10 times the log of that. So let's go ahead and jump right into the practice problems that I gave you guys. Okay. And that is these problems right here. We have a violin. All right. So violin is played and is producing a sound with a power of 0.15 watts. And That's probably not your max power of that violin, but you know, it's just ordinary playing, 0.15 watts. If you're 10 meters away, what is the sound intensity? How many decibels of sound would that be? And how many violins would need to be played to increase the loudness by 10 decibels? And an increase of loudness of 10 decibels is about twice as loud, okay? So as you increase 10 decibels, you are expecting something that seems about, you know, maybe twice as loud, more or less. All right, so let's go ahead and just jump right into this. 0.15, so that's our power. Okay. So that is the power is 0.15 watts. And we have a radius or distance of 10 meters. And so first of all, we want to know what's the intensity. All right, well, we know the intensity is simply going to be the power divided by 4 pi r squared. And so that's going to give us 0.15 watts divided by 4 pi times 10 squared. 10 squared, that's going to be 100 square meters. And let's go ahead and do that calculation. So it's going to be 0.15 divided by 4 pi or times 100. So let's just go and make it 400 pi. But if we do this, we're going to get the wrong answer. So if you go 400 pi, it's going to be the wrong answer because your calculator is going to see that as 0.15 divided by 400 times pi. So it should be 0.15 divided by 400 pi. And that is the correct answer, or it should be 0.15, and you can do it this way, divided by 400 divided by pi. Either way is going to get you the same answer, okay? And that puts your all your numbers down there in the denominator. So your answer is 1.19 times 10 to the minus 4. 1.19, and we only have two significant figures, so we'll just go ahead and make it 1.2 times 10 to the minus 4 watts per square meter. Watts per square meter. Now, we're going to go ahead and use that number in our calculator, and we're going to calculate the number of decibels it is. So to calculate the decibels, which is a measure of your loudness, right, your decibels, it's going to be your intensity divided by, 1 times 10 to the minus 12th, and all of that, you're going to take the log of all of that, and then you're going to multiply that by 10. Sorry, I ran out of space there. So your decibels is going to be 10 times the log of your intensity over 1 times 10 to the minus 12. So we're going to take that intensity and divide by 1 times 10 to the minus 12th. And that's going to get us a fairly large number. But as soon as we take the log of it, it's going to be significantly smaller. And then we're going to multiply that by 10. So right now, if we wanted to know just the loudness in general, you could say it's 8 bells of loudness, or 8.07 or 8.08 bells. But you have to multiply by 10 to turn it into decibels. And so it's 80.8 or 81 decibels. 81 decibels. Okay? And that's a little bit more of familiar units for us. So decibels, the more, you know, the larger the decibels is, the louder it is. And it's kind of a range that we're familiar with, right? 0 decibels is going to be at the threshold of hearing, and 100 decibels, if you're wondering, okay, where's your threshold of pain? So 100 decibels is going to start to hurt, or 120 decibels is going to really, really be painful, okay? So you have that kind of 0 to 100 range there for your decibel scale of hearing loudness. Next up, what is the sound intensity of a sound that is 75 decibels? Well, how do you do this? We know the decibels, but we don't know the intensity. So let's go ahead and write out that equation here. So your decibels are going to be equal to 10 times the log of your intensity over 1 times 10 to the minus 12th, right? And so what we want to know is, well, what's the intensity? Because we know the decibels already. So what we're going to do is we're going to, first of all, divide both sides by 10. That's going to be the first thing we're going to do, okay? And so let's go ahead and just put their number in. So we have 75 here, right? So you're 75 decibels. And we want to first convert that to bells. So we divide both sides by 10. So that's going to get us 7.5 bells. And that's going to be log of your intensity over 1 times 10 to the minus 12th watts per square meter. Okay? Still, we're trying to solve for I. So how do you get rid of the log? Log is, of course, the inverse of the exponential. And your general log in this scale is a base 10 log. So we haven't been writing down the base of this, but anytime you use the log, the log in your calculator is always base 10. So this is base 10 log, which means that the inverse of your base 10 log is 10 to that power. So to get rid of the log, we're going to do 10 to the power of both sides. So that's going to be, just coming over here to this side, that's going to be 10 to the 7.5 equals the intensity. So 10 to the log is going to get rid of the log. Intensity over 1 times 10 to the minus 12 watts per square meter. So we're almost there. Now we need to multiply both sides by this 1 times 10 to the minus 12th. That's going to get us 10 to the 7.5 times 1 times 10 to the minus 12th watts per square meter equals your intensity. And we could just plug that right into our calculators, or we could do a little bit of exponential math if you're interested. You don't need to. So, you could just plug this right in your calculator and you're good to go. Or I could recognize that when you multiply two different things here, you just add the exponents. So it's going to be negative 12 plus 7.5. So that works out to be 10 to the negative 4.5 watts per square meter is equal to the intensity. So we can plug either one in our calculator. I'm going to go ahead and do 10 to the negative 4.5. That's going to be our final answer. And that's going to be 3.16. Your intensity is 3.16 times 10 to the minus 5 watts per square meter. Okay? And so you can convert from decibels into intensity or from intensity into decibels. You should be able to go back and forth. And in general, it's going to look like this, right? So in general, if you want the intensity, you can generally say that your intensity is going to be equal to 10 to this, this was originally 75 decibels, right? So that's going to be negative 10 to the negative 12th plus your decibels divided by 10. Okay, so that's essentially what we did, right? So your intensity is going to be 10 to this power, negative 12 plus whatever the decibels divided by 10. Okay? All right. So that's it. You guys have the rest of, our class is pretty much over anyway. But are there any questions at all? I'm sorry, we got cut off, several times during this class. I don't know my internet looks like it's going fine. I actually think this is probably a problem of YouTube. So, but that's I don't know. I don't know what happened today. Anyway, any questions at all? I don't know if is anybody still even with me? I got 8 people. 8 people. Awesome. Questions? Anyone? Or chess? Anyone? So I'm done going over stuff. You guys can do the rest on your own, and we will solve the other ones together. All right, so sorry. So Adam, you want to go? All right, so let's do chess, and everybody else, bye. I'm just going to log off of this one. So, boom. With no other questions, it's goodbye.